Welcome to lecture number 7. In this lecture, we review the concepts of classical field theory. So recall that in the last lecture, we reviewed classical Lagrangian mechanics for a point particle. So in this lecture, we want to generalize the treatment from the point particle to classical field theory. The point particle is a concept where we have something that's localized at one point in space. Field theory, by contrast, is a concept that applies to a field, so something that's extended in space. So it can, in principle, extend over all of space. It does not need to be localized to a point. Real-world examples of field theories, or fields in general, are the temperature field, the temperature as a function of time and location, which is simply the temperature at a position x at some time t. The temperature is an example of a field, even though it's a non-relativistic scalar field. Another example for a non-relativistic field that is different from the scalar field is the wind field, vector v t of x, which just is the wind, including its direction, at a position x in space and at a certain time t. And the difference with respect to the temperature field is that the wind field would have 3 components at every point in space and time, instead of just one component like the temperature field. So that's the difference between a vector field and a scalar field. In the following, we want to talk about relativistic field theories. So we will consider fields that are relativistic, even though it's perfectly possible to set up non-relativistic field theories. How do we go about this? So let's get started with the point particle in one dimension, which has a single coordinate as a function of time, x of t. If we now consider the point particle in 2 dimensions, and we do this in index notation, so with an index I that runs from 1 to 2, it has 2 coordinates, x1 of t and x2 of t. Now let's generalize this concept to many dimensions. So not just 3 or 4, but n dimensions, with n being much, much bigger than 1. We can again write the particle's coordinates, xi, in index notation, where I now runs from 1 to n. Or alternatively, we can change notation, nothing else, and say that we define something that's called phi, and that phi depends on t and x of I, which is just writing xi of t in a different form. So we sort of take the time t as being one argument of this function phi, and the coordinate which we consider as the second coordinate of this field phi. If we now take the continuum limit n going to infinity, then the continuum limit of this notation phi of t and xi can be written simply as phi of t and x, where x is now a continuum variable that ranges from -infinity to +infinity. It is, if you want to, the continuum limit of having many, many coordinates in which this one point particle can live, and it's taking this to extreme by saying we have an infinite number of possible coordinates, and then what we get is this one-dimensional field theory. So this field phi now is now a field that depends on time and this new coordinate x. And in this case, basically, it's a field that is 1 + 1 dimensional, 1 time dimension, and 1 space dimension. So we call this a 1 + 1 dimensional scalar field. It doesn't have any vectors in it, so that's why it's called a scalar field. It's easy to generalize this then to even higher dimensional fields. So this would be a field phi that depends on time and more than just one coordinate, let's say 3 coordinates, for instance. And this would be an example where we can make a 4-dimensional field theory. Phi just depends on x mu, where x mu is our 4 coordinate ranging from time over 3 space coordinates. Instead of writing phi of x of mu, I will also often just write it as phi of x, where x now just collectively denotes all the coordinates that we have in our spacetime. Okay, so we talked about the action in the case of classical Lagrangian mechanics. Now we sort of take the same concept and we want to construct classical field theories, in particular relativistic classical field theories. In order to do this, we want to proceed by constructing classical action S that is obeying some of these fundamental symmetry requirements that we would like to have. In particular, if we want to construct a field theory that's invariant under special relativity transformations, so if you want to naturally incorporates the symmetries of special relativity, then basically that symmetry has to be something that's obeyed by this action S that we want to write down. In special relativity, we know that time and space are not independent, so we cannot write an action as being the integral over time of some Lagrangian, simply because time is not invariant. It is simply not a good starting point. So we need to change the setup for our action because dt does not transform properly under Lorentz transformations. However, we know how to replace this. We know that we have to lump space and time together to space-time. And if we do this, then we can consider an object that takes the space-time volume dt d3x, or compactly written as d4x, as one building block. So this four-dimensional space-time volume d4x is invariant under Lorentz transformations. And as such, we can write down the action for classical field theory that is the integral over d4x times now something that generalizes the Lagrangian. It is now not a Lagrangian, it is now a Lagrangian density because we integrate over space as well as time. And that will be the form of our action that we need for our field theories. In order to set up a proper relativistic field theory, we now need to declare the content of the field theory. So we need to ask ourselves, what do we want to describe? Do we want to describe scalar fields, like the temperature fields, or vector fields, like the wind field, or maybe even tensor fields? The simplest case that we can start with is a scalar field, which we again denote by phi of x. And this corresponds to a single degree of freedom at every point in space of time. So this is why it's called a field theory rather than just a point vector. So given the field content, we can then proceed to construct the Lagrangian density L from the field phi and its derivatives. At this point, the only rule is that the Lagrangian density L must be a scalar, otherwise the action will not be a scalar. And it must be scalar under certain properties of coordinate transformations, which in our case are special relativity coordinate transformations. So the way this plays out is that we know that if the Lagrangian density L contains combinations of the field phi and derivatives of the field phi, which I write as d mu phi, then possibly allowed terms that transform as scalars under special relativity transformations are things that carry no free indices. So an example would be phi squared, the logarithm of phi, the exponential of minus phi, d mu phi with the index summed over because this is also a scalar, d mu d nu d rho d rho phi because here all three indices are summed over, or similar examples. On the other hand, terms that would not be allowed are things that are not scalars under special relativity transformations, such as d mu phi on its own, d mu phi d rho phi, because this has a free index d rho, or other things that don't carry any, other things that carry free indices, basically. To simplify the discussion, we will limit our discussion to theories with Lagrangians that are of, if you want so, canonical form. Okay, so these are things that have two derivatives, d mu phi, and a potential v of phi, which is simply a function of the field phi and no derivatives. For Lagrangian densities of this form, the action will then be given by S is minus d4x of the Lagrangian density. And we can again find the equations of motion by demanding that the variation of the action is 0 for an arbitrary change in coordinates. So one finds the equations of motion for the field phi, following exactly the same rules that we had for the Lagrangian point particle. And in this case, we have the equations of motion being dl by d phi minus d mu dl by d mu phi is 0. So note that the derivative with respect to coordinates d by d mu replaces the time derivative that we had in the derivation of the equations of motion for the point particle. For this particular form of the Lagrangian density, this becomes minus the derivative of the potential minus d mu phi. And in the following, I will sometimes denote this operator d mu phi as a box operator. This is sometimes pronounced the Quabbler operator, which is simply a wordplay on the nabla operator di, the Laplacian that we have in usual sort of three-dimensional spaces. Finally, before concluding the lecture, I want to point out that we can consider more complicated field theories. So I already alluded to the fact that we can think of vector fields or tensor fields. In this case, I want to remind you that we can also consider a case where the field phi itself is a complex field. So it's no longer real, but it's complex. So it has a real and an imaginary part. We can again construct a field theory by considering an action that is Lorentz invariant. And in addition, we want to require S to be real. If we denote the complex conjugate of phi by phi star, we can fairly easily find an action that fulfills these properties. For instance, it's given by d mu phi star plus a potential that is a function of phi star. And that has the property of being Lorentz invariant because all the indices are summed over. And it has the property of being real because every quantity here appears times its complex conjugate. So we get manifestly real Lagrangian density. So this is an example of a real and Lorentz invariant action for a complex scalar field. Again, the potential here is again arbitrary. But we can be very concrete. We can sort of write down a particular potential. Turns out it's particularly convenient to talk about polynomial potentials, so things that have only polynomials of the argument, no logarithms, exponentials, or other functions. And a sort of fairly common potential that we can think about is something that has m squared phi star plus 4 lambda times phi star squared. So if you want, so this is something like a quadratic term, and this is something like a quartic term. And we can interpret with a little digging, we can interpret this parameter here as being the mass squared of the field, and we can interpret this quantity here as the coupling constant of the field. And this concludes the lecture.